Okay, so in this presentation, we're going to take a look ahead at the concepts we're going to cover after this next exam. I just want you to get a general feel for the topics that we're going to take a look at. So don't feel like you need to understand everything in this one video. So one thing that I want to bring up first off is this concept of the mean square. Mean square is actually a concept that we have seen before. It's been known under a different name. And if you look at the equation for mean square, which is a sum of squares over degrees of freedom, you will recognize that as what? That is variance. So when we do ANOVA, which is an acronym that stands for analysis of variance, we use this concept of the mean square to represent variance. And when we say analysis, we're breaking something apart. Lysis is a root word that means to break apart. So analysis of variance is to take the variance that is in existence within an experiment and break it apart into constituent parts, and we'll see which parts that we are going to break it into. But you want to recognize this concept of the mean square, and you want to know that that means the mean of the squared deviations from a mean. Okay, so it sounds kind of complicated, but if you understand it, that's a simple thing to think about. You have a bunch of data points, you have a mean. Each data point has its own distance from the mean. If you square each of those distances and then add those squares together, you get a sum of squares. That's the sum of squared deviations from the mean. And then if you divide that by the number of scores that you had, then you got sort of the average squared distance from the mean, right? So that would be the mean of the squared deviations from the mean. So that's what mean square means, okay? Now when we're looking at ANOVA, the mean square, we're going to break into two parts, okay? One is going to be the between treatments mean square value, and the other is going to be the within treatments mean squared value. And once we get those two values, we're going to have a new statistics which we call the F, okay? And F is the mean squared value for between treatments divided by the mean squared value within treatments. And if you see a fraction, this should automatically have you thinking, what do we think of fractions as? What do fractions signify for us? And fractions signify a perspective. We're looking at the what from the perspective of the what. We're looking at the numerator from the perspective of the denominator, okay? So we're looking at the between treatments mean square from the perspective of the within treatments mean square. So then you might expect that the within treatments mean square is some sort of standard value that we're comparing the between treatments mean square with. Okay, so again, I asked you to remember a fraction can look at the numerator from the perspective of the denominator. So now let's look at what we mean by sum of squares within and mean squares within and between treatments, okay? We can look for a sum of squares total, okay? Let me just walk you through what this graphic is over here. We've seen something similar before. What I've done is I have two samples. There's a red sample and there's a blue sample. Okay, the red sample consists of 3 scores and the blue sample consists of 5 scores. Now for the 3 scores in the red sample, I've calculated a mean. Okay, so that sample consists of the numbers 1, 2, and 5, and the mean is 4. So each score from the sample has a distance from the mean. Okay, so this distance of 4 units would be the distance of this score from the mean. This distance of 2 units would be, this is 3 units. This distance of 3 units would be the distance of this score from the mean, and this distance of 2 units would be the distance of this score from the mean, and this distance here of 1 unit would be the distance of this score from the mean. And I've made squares out of them to signify for you that we're talking about squares, okay? So you can think about these as a square distance from the mean within this treatment, right, which is the red sample. And then I've done the same thing for the blue sample. I've seen a sum of all of the squared differences from the mean for that sample. That sample has its own mean, okay? Now, I'm going to do one more thing, and that is I'm going to calculate a mean as if these were all just one sample, right? So I was thinking of them as two individual samples, and each sample has its own mean, but what if I thought about it as one larger sample? Then I'd have a new mean, and that would be somewhere around, I don't know, 6.6 or 8 or something like that, if I remember correctly. And then we could think about the squared distances from that mean, okay? And you can see those are different values. So each value of a squared distance we had for these scores within their treatments, we can also have a squared distance where we're looking at combining the treatments, okay? So for example, this square corresponds to this score, and the original square we had was here that corresponded to this score. This square comes from this mean here, and this square comes from this mean here. So I have three squares here. I've signified in red 1, 2, 3 squares, which correspond to the distances of those various scores from a mean that represents the entire sample, as if you thought of both of these samples as one. And do the same thing for the blue. And what I would call this, or what we do call this, is this total sum of squares, okay? And that's the total sum of squares, not taking into account that these were separate samples. Just think of them as one big sample. Over here on the left, I want to remind you that we had an idea of a within treatment sum of squares, okay? And we used this when we looked at like pooled variance and so forth. I want you to look at it again. We also talked about it when we talked about R squared, things like that, which we'll talk about more. So you can see what I did was I took these 4 blue scores, right, correspond to these scores over here, and these 3 red scores correspond to these scores over here. And what I did was I just pretended, let's just think about them in terms of distances from their means. Let's pretend they had the same mean, okay? And that would give us a graphic that looks sort of like this, okay? This, if you added all of these squares together, this circle represents 0 distance from the mean. If you added all of these squares together, it would be as if you were looking just within the treatments, okay? So this represents the sum of squares within over here on the right. Now, what are we doing when we look at analysis of variance? When we look at analysis of variance, we can add another sample. The reason we do analysis of variance is because unlike with a t-test, where we can calculate a difference between 2 means, when you have 3 means, you can't use a t-test because you could compare 2 out of 3 means each individually, but you can't get some general sense of if there's a difference between 3 means, or a significant difference among 3 treatment means. Okay, and that's what we want to do when we're looking at ANOVA. And we'll go into various reasons why we need to do it that way. It's less repetitive. We don't have to go through each individual comparisons to see if there's a significant difference. And also, we do ANOVA to minimize the chance of a type 1 error, or to at least account for the chance of a type 1 error when you do repeated experiments. So if you look at my image here, I've still got my 2 initial treatments, okay? But now what I'm doing is I'm calculating a new mean, right? Because I have more values, I have a different mean. And this mean is very close to the mean of this blue middle treatment here, but it's not the same. It's a little bit to the left here. And what you can see is that if I stack the mean differences here, the squared mean differences here and here and here on top of each other, I can look at them all like this, as if they all had the same mean, but we're just looking at the differences. And I would call that the sum of squares within treatments, okay? This is sort of like what we do with pooled variance, okay? With pooled variance, we had all of the sum of squares within 2 treatments, and then underneath that, we add all of the degrees of freedom within those treatments. And we get a a mean squared value for that, and we call that variance, pooled variance. So sum of squares within would look like this conceptually. And what we're looking at here, we would call this sort of sum of squares total. Okay, so we're taking all three treatments into account as if they're one sample. Okay, one sample of, what is this, 5, 8, 9, 10, 11 scores. Okay, and I've represented just the largest deviations from that mean for you. If we could go on and list all 11 deviations, but you could see they'd be large squares, and I don't have room for that on this page. So I've taken, what's the largest deviation from this sample? Well, that would be this one, right? That's the farthest from this mean here. And this is the largest deviation from the mean and from this sample, right? That corresponds to this score, this initial square. And then have a square that represents the largest deviation from the mean in the green sample. Okay. Now, again, SS total would consist of more than these three scores. There'd be 11 squares and would continue to go down to the bottom of the page. These are just, I'm just representing SS total by the largest deviation from each sample. Now we can think about one more idea, which we're calling sum of squares within. Okay. Now, what sum of squares within? No, we're not calling it sum of squares within. I'm sorry, that's a typo. Sum of squares between. This should say sum of squares between. Let's just correct that. Excellent. And slideshow from current slide. Okay, so this is what we're calling sum of squares between treatments. Okay, what we do here is we still think about this mean that we would get if we thought of all of these treatments as one sample. But now we take into account that we can have a deviation to the mean for each sample that corresponds to the mean for that entire sample. And I'll go into this in a little bit more depth. So I think I've talked about this before in class. You can think about this in the following way. You can have a mean for the entire group of samples, right? And you can think about, how would I get to this score? Say we're talking about this red score at 5. What's a way that I could get there? Well, I could take a trip to the mean of its sample, and then I could take a smaller trip over to its specific value. So I would have two trips. I would take a trip that corresponds to the mean, and then once I get to the mean, I would take a small trip to get to that actual score. And I can do that for every score in that sample, right? I could take a trip to the mean, one larger trip, and then take a smaller trip to this score, or a smaller trip to this score, okay? So we can think about it in this way. We can think about getting to each score in each of these three samples now by going to their mean first, okay, which would be a larger trip, at least in this case, be a large trip, and then just taking a small trip to get to that specific score. And it's sort of like compressing the information. It's saying, yeah, there's a general value that I can get to that will get me close, okay, but then I can get to the specific score in each of the samples, okay? So what I did was I made 3 boxes here, okay, but I want to highlight here that each sample has a squared deviation, which is multiplied by the sample size. So what I'm saying is, in order to get to all of these values, I have to go to this square, right, and I have to go to this value. I have to go to the square again, and then I have to go to this value, to go to this square again, and go to this value. So I've gone to this distance 3 times to get to these 3 values. So I've only listed each of these squares once. But the sum of squares between would be the sum of these squares times 3, plus the sum of this square times 5, right? Plus this square times 3, okay? So that's sort of a way to conceptualize a sum of squares between. Again, if you're not getting all this, that's fine, but I do want you to pay attention and have this in your memory as a way to think about what's going on. Because you're going to remember a lot of equations, and you may get lost. You may get disconnected to the concepts which the equations represent. I'm trying to give you the concepts which the equations represent before you have to spend too much time taking a look and trying to work with the equations. Okay, so that was what we would call just simply ANOVA, or one factor ANOVA. And in the next chapter after that chapter on ANOVA, we're going to look at two-factor ANOVA. We'll skip chapter 13 and we'll skip to chapter 14, two-factor ANOVA. So we have a similar situation here in which we have several different treatments. Okay, you can see I'm representing each treatment by a cell in a group of boxes here, okay, and one box with cells in it. So you can imagine you did a treatment where you had a sample mean of 7, a treatment where you had a sample mean of 9, a sample mean of 3, a sample mean of 5, and here's another circumstance, okay? What this represents, you'll see this in this chapter, is two different versions of one experiment. Basically, in summary, you had people with low self-esteem or high self-esteem, okay, and you gave them some tests they had to take, which they would get a score on. But you also put those two groups in two other different situations. One, they might have an audience watching them, so somebody keeping an eye on them, or they just get to take some sort of test on their own, right, without anybody watching over their shoulder. And we're looking to see if either of these factors has an effect on their score, right? Does their score depend at all on their level of self-esteem? Does their score depend at all on whether somebody's watching or not? And then there's one more thing that we can look at when we look at two-factor ANOVA. And if you haven't realized by now, the two factors are whether or not there's an audience, that's one factor, or what the level of self-esteem is, low or high. The one thing that we can look at now when we have two-factor ANOVA is if there's an interaction between the two factors. Meaning, for example, yeah, it matters whether there's an audience, but only if you have low self-esteem, right? Otherwise, high self-esteem people score about the same, for example. And that's kind of what we're looking at over here. So here's one situation. I want to show you how to read this plot here, okay? This line in general just represents all low self-esteem conditions, okay? So any low self-esteem condition is on this line. And this line represents all high self-esteem conditions, okay? And then we're comparing, is there an audience or not? Okay, so here's no audience and here's an audience. So basically what you're seeing is that there is some sort of increase in score based on whether there's an audience or not, right? There's an audience, there's a higher score generally, right? You see this is consistent whether you have low self-esteem or high self-esteem, okay? And then you can also see an effect that is signified by the distance between these two lines. So in general, the high self-esteem condition has lower scores, okay? 3 or 5 as a mean, as opposed to the low self-esteem condition. I think I said this properly. The high self-esteem condition generally has lower scores than the low self-esteem condition, which generally has higher scores. Now, what we're seeing over here is it's just the same experiment, but thinking about another possibility in the way things could turn out. So, for example, you could have some sort of effect, okay, where there's a difference, whether you have an audience or not, but only if you have low self-esteem. If you have low self-esteem, then your score, we're guessing this is your higher score means you did worse on some test, right? Generally low self-esteem, if somebody's watching, then you're really gonna screw up. But if you have high self-esteem, you'll be consistent, okay? And this means there's some sort of interaction, okay? Yeah, the high self-esteem condition is generally has lower scores than the low self-esteem condition, right? But there's also some interaction here that whether you have high self-esteem or low self-esteem matters if you're looking at whether there's an audience or not. And this is some of the advantages of looking at two-factor ANOVA. Now, we talked in one-factor ANOVA about the mean squared value. We had MS between, MS within. And now when you're looking at two-factor ANOVA, you need to know that there's an MS between that gets broken down into 3 distinct parts, okay? And those parts consist of on MS for the A. Okay, so in this case, most of the time we're looking at A would be, I don't know if I'm getting this right, but you could switch them around. A could be the columns, for example, no audience or audience. So there's a factor A, right? So we might get an MS value, which is represented by the sum of squares within the A, or between the A treatments. Okay, so that would be like the sum of squares represented here versus the sum of squares represented here. And then you could have the sum of squares or the mean squared value for the B treatments, right? So you're looking at these two treatments versus these two treatments, right? Or you could have some interaction. That's the kind of case that happens here, okay? The mean squared value. Again, we're just sort of looking over this stuff. I just wanted to get it into your head, get these terms in front of your eyes so that you can start to feel comfortable with them when you look at them later. Okay, let's move on to correlation. This is the next chapter we'll look at. Now I'm going to introduce you to another new term. We had sum of squares. Now we're talking about the sum of products. Okay, and I'm going to show you a little visualization to understand what the sum of products, a way to think about the sum of products. So what we do with the sum of products is we have matching scores from two different samples. Okay, so for example, height and weight, let's say. You know, I have a height of 6 feet and a weight of 180 pounds or something like that. I have a height of 5 feet and a weight of 120 pounds, okay? So each set of scores are matched, okay? And we're looking to see if there's some sort of correlation. You may be familiar with the term correlation. A simple way to think about it is if there's a correlation when one goes up, right, then the other one goes up. Okay, so you might have a higher weight if you have a higher height, for example. And you could also have an anti-correlation, right, where one thing goes up but the other thing goes down. Okay? So let's take a look visually at this kind of idea. So we need to understand the concept of sum of products. So let's say that this represents the mean of x values. Let's say these are heights. Okay, so I have a height here, a different height here, a different height here, a different height here. Whereas we're looking just in the up and down, we're looking along the x-axis, okay? And then we have some values that we correspond to the y-axis, okay? So we have value here, 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 and here, okay? What we're doing when we look at the sum of products is we're taking corresponding x and y values and we're multiplying them, okay? So for example, here I had two positive values, I multiplied them. Here I had a negative value for x and a positive value for y, I multiplied them together. Here the same thing happened. Here I had a positive value for x but a negative value for y, okay? Positive x, negative y, and here both were negative. And what we do when we do the sum of products is we basically take all those rectangles that we would create by looking at things this way, and we add them together. And you can see that all of the red rectangles represent negative numbers. Okay, I multiplied a negative by a positive or a positive by a negative. And all of the blue rectangles represent positive numbers. Those could happen for values in this quadrant or this quadrant, right? If I multiply two positive numbers, right, versus if I multiply two negative numbers, I can, both those situations, I can get a positive number. If the sum of all of these things, if you take these values and subtract these values, if they're about the same, you're not going to have a correlation. Okay, so you can see in this situation, the overall area contained within these red squares is about the same as the area contained within these blue squares. Okay, I'm going to have to plug in my computer, so we'll take a pause here.